I will talk to you about pushed-in piles. So what's the context of this research? Basically, the most used method to install piles at the moment is pile driving, which, as you know, is quite noisy and may be harmful to marine life. So there are mitigation methods that exist, but they are not necessarily cheap. This is why we propose to use this concept, which is a pushed-in pile concept, where a cluster of 4 smaller piles replace a larger pile. And those smaller piles are jacked. One pile is pushed at a time by a stroke of half a meter, while the other 3 may serve as reaction piles. Now, what's the objective of this work is to provide experimental evidence that the concept works, identify the mechanisms underlying installation, and predict refusal. This is based on a range of centrifuge tests that were undertaken at the University of Dundee by Yassine, Craig, Scott, and Mike. You can see the setup here, where you have a sandbox and you have servo motors which control piles individually. And all of the details of this are published in this paper that should be available soon. Now, if we have a close-up, you have the 4 piles here. Each pile is instrumented with a strain gauge, and they pass through a guide plate, and there are 2 different spacings, basically, very close or a bit further away. Overall, these were 38 centrifuge tests in medium and dense sand, various loading rates, various diameters, etc. Now, what's the typical behavior of this cluster? In this figure, you see the penetration resistance as a function of depth, and you have a single pile, this is the gray line, a pile as a part of the cluster, this is the blue line, and the sum of the forces in all 4 piles, this is the red line. So we have 3 phases. The first one here is just a synchronous phase, or self-weight penetration. All piles move together downwards. Then we start the cycling. When those piles reach the total force of the reaction force, which is the tool of the weight for self-penetration, then they stop. Then we start this asynchronous, where we push one pile and the other 3 are moving up. You can see that from this depth, the sum of the forces in all the piles is a constant and equal to the reaction weight. Now we can see here all the cycles as a pile is pushed and unloaded, pushed and unloaded. And during this phase, there is no tensile resistance mobilized. It's just the unloading of the pile and the reaction forces rebalanced onto the other pile. Then we have a third phase where we mobilize tension in the pile, which becomes a reaction pile when the other piles are pushed. And what we can see here is that the net stroke, so the stroke after the pile has been pushed and then after it has been unloaded, this net stroke is reducing and reducing and reducing. So we need something to quantify this. And this is the efficiency. So the efficiency we define here as a net stroke, so the actual penetration of a pile after being unloaded upwards, divided by the length of the stroke, which is half a meter in this case. Now, if you look at the efficiency, it starts close to 1 and then reduces almost linearly. At some point, this efficiency can fall very close to 0, in which case we have refusal. Now, in the following, I will just show you the envelopes of tensile resistance and compressive resistance here, because it's easier for the different figures. Now, plugging is also central in the behavior of this pile cluster, but I don't have the time to discuss it. But, however, it's in the paper. Now, in terms of physical mechanisms, what is happening, we have first coring and plugging. So if this is just a single pile, these curves are just meant for a single pile. You have some coring here, you have some concavity, and then plugging, and this is the tensile resistance of the pile, the compressive resistance of the pile. First phase, all piles are moving together, so if you want to move the soil, it has to flow around the entire cluster rather than the individual pile. So in general, the penetration penetration resistance of one pile will be greater. Then you have this phase where all piles are moving cyclically, but still there is no tensile resistance. However, each pile adjacent to the pile being pushed will create some constraint because there is a higher stress, but lower than under the pile being pushed, but still. So there is some asymmetry in the way particles are moving. And then in the last phase, because the other piles act as reaction piles, they are moving up. So they create a very low stress zone underneath, and that will mean the pile, the soil underneath the pile which is being pushed can somehow recover the one of a single pile. We recover some form of symmetry. So what we need to predict is the enhanced penetration resistance of one pile as part of the cluster, the enhanced mobilized tensile resistance, because in between we have enhanced radial stress, and then changes in efficiency with steps. Okay, how did we do this? Basically, we have a CPT prediction method that uses the input, the behavior of a single pile, so compressive resistance and tensile resistance as a function of depth. And you can use any method for that, like the unified CPT method, and you just need something more for the plugin. And the output will give you the behavior of the pile in a cluster and the changes in efficiency. Now, this is all based on the fact that we have equilibrium. So first, we have the total reaction force. And the total reaction force after any stroke is simply equal to the weight of the tool and the tensile resistance of a single pile multiplied by a factor. And this factor, we have back calculated it based on our centrifuge tests and plotted it against efficiency. So this is an example here for a spacing of 1.5 diameter in medium dense sand. And we have 0 here because there is no mobilized tension for some efficiencies, and then we have some mobilized tensile resistance, which is greater than 1 because there is some enhanced radial stress over here. Now, at any time, this reaction force is equal to the penetration resistance of one pile part of the cluster. And this is equal to the compressive resistance of a single pile multiplied by a factor. And again, this factor we have back calculated. When the efficiency is high, there is not much movement between two adjacent piles. So there is a high constraint on the side of the pile, and the penetration resistance is higher. And once the efficiency drops, then this factor tends to go to 0 because we have lower constraint. And then we have one equation that is a function only on efficiency. So this can be solved. Now, this is what we get. This is the example. We have the experiment, which is denoted by markers here, and we have all the solutions, which are given here as solid lines. And you can see that we have a pretty good fitting. There is one pile which actually encountered some refusal, and the other ones, the experiment was just stopped because the pile was too short to continue. If we look at the efficiency, we have the red one which reached refusal, and you can see that the efficiency was tending towards 0. Now the interesting part is that for the other ones, the other piles could actually, they hint that there may be some efficiency recovery. And this is because the reaction force depends on the integration of stress along the shaft, while the pile tip just depends on the diameter and the QC value at the depths of penetration. So there may be some form of optimum combination of length, reaction tool, and pile diameter, where actually there is endless reaction force and we can keep pushing the piles in. Now, what we can do is simply trace for a given tool weight what is the penetration depth for the pile diameter. And this is the curve we have here. This is the dark blue. The dashed line means there is no refusal, but the penetration was just stopped at 17 meters as per the test. And the markers are the ones that come from the centrifuge, and they match more or less the curve here. We can also plot the penetration resistance that corresponds to this final depth there, and this is a proxy for the behavior of the cluster. And again, these are the dots are the centrifuge tests. Now, what that means is that for a given target force, there are two pile diameters that can match this target force, because you have a smaller diameter which will go further down, or a larger diameter that risks refusal, but they would give you both the same penetration resistance. We can also start varying the tool weight, and by varying the tool weight, we can start optimizing. So a smaller tool weight will give you refusal for a smaller diameter. But then, for the same target final penetrate or reaction force or resistance, you may have two pile diameters corresponding to two different tool weights. So overall, this is just a tool for optimization. And we can then have the best cluster possible that will be the best combination of operational constraint, like the tool weight, and pile dimensions. Now, as a conclusions, I just wanted to demonstrate by this set of extensive centrifuge tests that the pushed-in cluster concept can be working, can be very efficient, because we can jack clusters up to 5 times the penetration under static weight alone. And eventually we have come up with a method to predict the pile refusal and estimate penetration resistance. And all of this will be published in this paper, which should be available online pretty soon.